Hi everyone, welcome back to Cody's Lab. So this is a shard of gallium metal, and this here is a piece of indium metal. Gallium melts at about 30 degrees centigrade, and indium melts at 157 degrees centigrade. Gallium should be able to melt at body temperature of 37 degrees centigrade, but I've never really actually gotten it to do that, at least not in my hand. If I take these two metals, which are solid, and I combine them, look what happens. A liquid is formed. In fact, these two materials, when they're combined, they form a eutectic alloy which melts at 15 degrees centigrade, which is liquid in my hand. In fact, this is very similar to adding salt to ice in the way that this causes it to melt. You're forming a material which has a much higher entropy, and thus it's harder for it to form perfectly arranged crystals. Basically the second metal gets in the way of the crystal formation of the first metal, and that causes the randomness to be a little bit more, and so it's liquid down to a lower temperature. Now I can actually feel that the metal got colder. If we watch this happen with a thermal camera, you can see the metal here, and now let's combine it with the indium. Now you can't really see much happening because the metal is mostly just reflecting and showing the temperature of the room. But if I add a bunch of this and let it cool off, you'll be able to see that my hand underneath the metal has cooled significantly. See this spot here? It's actually making it cold. Now of course this is only taking it down to about 15 degrees centigrade. As the solid metal liquefies, it absorbs energy. Theoretically, it will absorb enough heat to lower its temperature down to its freezing point, which I can lower by adding a little bit of tin down to 10 degrees Celsius. As you can see, the tin actually broke as the gallium alloy combined with it made it brittle. So yeah, this now actually feels much colder. So this would just barely be liquid at room temperature at 11 degrees Celsius. Now I can lower the temperature even farther by adding some zinc. So there's some zinc right there, and some bismuth right there, and a little bit of antimony. So all these materials combine to make an alloy known as gallium, which is liquid down to negative 19 degrees centigrade. So here's a little bottle. Let me just take this gallium and first of all kind of bend or break it into a shape that'll fit down in here. Now when we add the thermometer, we should be able to stir this around and observe a temperature drop. Of course the thermometer did just increase because I touched it with my fingers. So there you go. It has dropped to about 1 degree centigrade below room temperature. It's honestly not as much of a change as I was expecting. I think it's mostly because the reaction is rather slow. It doesn't dissolve very quickly. And the heat of fusion and heat capacity of metal is much lower than, say, for water ice would be. You see now that I've taken the thermometer out, it has come back up to room temperature. So now I've transferred the alloy into a test tube here. There's still some chunks of other metal, tin and indium in there. So I'm going to warm this up to get it to dissolve a little faster. Basically melt the metals together. So now that this metal is cooled off, it's safe for me to pour it out onto my hand. There we are. Some liquid metal. Now for storage, I'm going to pour this metal off into a plastic bottle. It's very important that the bottle be plastic, because if this does freeze, it expands and will break the bottle, and I've had that happen. There we are. There's our gallium. In case you're wondering, this here is the composition of this alloy. Now if you're like me, the first question you might have after making a liquid metal alloy like this is what happens if I mix it with another liquid metal alloy? In this case, NaC. This is a sodium-potassium alloy, which was made in pretty much the same way as the gallium. Now I've actually got it stored underneath of kerosene because this stuff is very reactive. In fact, if I drop some into water here, it instantly ignites and explodes. So let's see what happens if we mix the gallon stand with the knack. Okay, so let's put a drop of the gallon stand out on the table and a drop of knack right there next to it. Okay. Let's see what happens if I bring them together. Okay, they didn't react, at least not vigorously. Let's kind of mix them in a little bit. Oh yeah, it's solidifying. It's not completely solidified. You can see it is mostly solid now. Let's find out what happens if I drop it into some water. Let me pick it up. Ooh. Well, it ignited and burned, just like the liquid sodium would do, leaving behind some gallium metal there. Let's try some of this that didn't freeze. That did not react. So I just poured off the water. Let's pour this out and have a look at it. And it's back to being a liquid gallium alloy. So what I think happened here is the two liquid metal alloys reacted with each other to form an alloy which had less entropy and was able to crystallize easier. So the sodium reacted with the gallium, for instance, and it made something that had a melting point which was much higher. So basically the reverse of what happens normally when you add another metal. So normally you get like a V-shaped eutectic graph, but this must have had something that had a pyramid shape. Now to test this, I want to try with a larger quantity inside of a test tube, so there's less oxygen reacting with it, and I'm going to measure the temperature. I'm going to try not to touch the thermometer so that my fingers don't warm it up. And I'm going to add in the sodium. There it is. Okay, and now let's kind of stir it around with the thermometer probe. And let's see what happens. I might have got too much kerosene in there for them to make good contact. It is warming up though. See, if it is forming an alloy that is a solid and is not soluble in the liquid metal, then it should release the heat of fusion, causing the temperature to increase. And I think that's exactly what's going on here. Cool. And since there is a bunch of kerosene in there covering it, I know it's not oxidation that's causing it to heat up. My other camera died, so let's switch to this for a little while. Yeah, it's already heated up to 16 degrees centigrade. Stir it around a little bit more. Yeah, it is getting very spongy in there as that metal is solidifying out. So it's basically precipitating from solution, if you think about it. So back to this camera. The temperature got over 10 degrees above the ambient temperature. That's kind of cool, watching that happen. The heat of solidification is definitely there, and actually looks like the whole thing is solidified now. I mean, it's not really solidified. I think there's still an excess of the gallium alloy. Yeah, you see it's running out of the mixture. See if we can get this sodium, potassium out of there. There we go. I should be able to actually give this a squeeze and squeeze out that metal. Yeah, so yeah, I'm squeezing out the gallon stand and I'm retaining whatever it is that is reacted. So it's probably a gallium, sodium, and potassium alloy here, which is not liquid. So this stuff does react with water. I'm going to add it to the water kind of slowly. Not all at once. I don't want too big of an explosion here. Hydrogen. Alright. So that's probably most of the sodium and potassium gone. Oop. There's a little bit of the potassium that is stuck to it, per se. Yeah, but for the most part, this is just the gallon stand right now. Probably a little bit different alloy composition since something got used up with the sodium. Let's actually pour a little water out onto it. Yeah, so there's just basically some of the potassium sodium containing alloy just sticking to it. Yeah, looks like it's all used up now. Let's put it back in the bottle. So here's the metal after the sodium has been burned out by the water. Well, at least most of it has been. If I push it back together, it looks like it will liquefy again, if it's not too badly oxidized. Yeah. Actually, you know what? This is not liquefying. Yeah, I bet what happened is the gallium basically has been extracted. Yeah, I think this is probably more pure gallium. It doesn't have as much as the indium and tin in it anymore. Either that or there's more indium. I'm not entirely sure what this composition is left over here, but it is definitely different. Actually kind of interesting how it's igniting as I rub it around on my fingers here. If I had too much more of it, this could be a problem. I think what's happening is the potassium oxides are reacting with the metal. Yeah, the potassium superoxide is forming. Can I strike it like a match? Alright. Definitely want to dispose of this so that it doesn't spontaneously combust on me. Yeah, things igniting is fine as long as you're expecting it. Okay, I think I got everything reacted with water. So, hope you enjoyed. I'll see you next time.